Hey, hey. All right, time to start, I guess. My name is Goran Mekic, or Meka for short, and I love telling stories. And I got a story for you today. The story is on operating system level containers and how did we get here and where here is actually, and what does my project has to do with it. Naturally, you're watching a Tilda Center podcast, and this is part of um, effort to expose more code to the, well, let's say public. Uh, we're all gonna try to learn here something, hopefully. And the story starts in year 1999. It's, well, uh, maybe it depends depending where you live and how old are you. The story can even uh, start fantastically because the story is fantastic. It's about running multiple operating systems on the hardware at the same time, and that's pretty insane idea. And we could even start a long, long time ago in a country far away called Denmark. The fellow called Paul Henning Kemp implemented the jails uh, for the current company he worked for, and they wanted to split the customers and to be able to run multiple versions of the same software. So he came up with this idea of jails, and next year in year 2000, the jails were part of a FreeBSD release that year. So in the year 2004, Sun and Solaris implemented zones. They're really cool containers. And rewinding to the year 2009, the Docker came out. So it kind of became popular until today that Docker is almost equal container. So it did a lot of job actually promoting containers as a concept, as something to be used, and well, something useful anyway. So uh, going forward, I mean, the Docker is not actually a container. It's using some of the Linux technologies to assemble containers or Docker containers as we know them. But I think before Docker came out, the Linux kind of wasn't that exposed to the idea of containers at all. In the year 2013, in St. Petersburg, the guy named Oleg Ginsberg writes the CBSD. It's well, back then it was a bunch of scripts he wrote to help him manage the infrastructure on FreeBSD. Today, CBSD is uh, pretty much used around the globe as a manager for jails and Beehive. Uh, it can run also Zen, but I I don't have experience running Zen anyway. So uh, the what happens after that is that I had a lot of annoying questions. I was annoying enough to end up with commit rights, and I'm part of a CBSD team. Um, I wrote the tool for helping developers and system administrators uh, develop and deploy their code. We're gonna see some bits and pieces of that today on because I'm using it to develop my own project called CBSDng, like as in new generation. Uh, and I have very few pull requests to the CBSD. I'm more whining to Oleg to fix it for me most of the time. Just kidding, but yeah, the CBSD is mostly Oleg. He's a lead developer and he's doing terrific job on it. And I'm most of my CBSD time is dedicated to reggae and other parts of the ecosystem. So this year, I was granted with a wish by organization called NGI, and they're sponsoring this project for a year. The project is called CBSDng, and it's to put it really simply, it's on one side a shell to control CBSD, and on the other is a web interface also to control CBSD. They are doing exactly the same thing, using different technologies and using different UI and displaying stuff, right? But um the project is aiming at making CBSD running and administrating easier, and as a consequence of web development there's going to be a REST API that can be extended for, I don't know, CI/CD for example later or something like that. So how about I show you what the jail is when there's let's say I have some jails here. Let me show you. All right. So I can list them. ls is listing files, so jls is listing jails, right? And kernel actually doesn't know what's a jail that is not running, so it's only showing the jails that are running, and that's, well, one in this example. Uh, but a CBSD knows how to display more than the jails that are currently running. And you can see I have quite a few jails here. They're for different projects and mostly development on this machine because, yeah, well, this is development machine. And there is no BLS for Beehive LS, but CBSD has that command because if I run something like this, it makes no sense. So the idea is that you have on one place called CBSD all your infrastructure, ideally, all your instances of jails and Beehive virtual machines. Uh, oh yeah, CBSDng only supports jails and Beehive because that's basically what's built into FreeBSD, and you get it for granted, right? Uh, they're with a default installation present, so why not? Now, what if I tell you that something like this is all that it's needed to run uh, all the services. Services are front end, back end, uh, daemon, and shell. Maybe in the future there's going to be a fifth one. I haven't decided yet. The one that's gonna execute the commands for the backend for the web. So I'm gonna cross that bridge when I get there. So what this produces and this little config file, uh, because devil mode is naturally it's important for development, and what it does is share the code and creates a devil user inside the jails that has the same UI and Git that your user running the command has. So the code can be shared really easily and you don't have to, I don't know, change own or something. Anyway, what this produces is this. Now, this is how booting of a jail with VNet that I'm gonna talk about some other time, but it's a really cool network technology. Uh, this is how it looks with CBSD, and you can see quite a few services now starting. All right, and now, well, the hell got broke loose. Now we see all kinds of things. There are uh, four. It's called pane, as in, well, let's call them windows. Um, if I show you like this, which one is which, you should see the numbers from 0 to 3. And it's something Reggae uses called Tmax, uh, terminal multiplexer. Uh, it's a way that whenever you hear multiplexing, it actually means you're trying to be cheap. That means that you're trying to get two for one or three for one or something like that. It's, I think, from uh, from the phone uh, that had first multiplexing. So it's trying to hook more than one line at a time through one wire, one physical carrier. So we're doing actually the same. We are having four terminals here in the boundary of a one, right? We're multiplexing. So yeah, we're cheating. We're being cheap. So number 0 is where the shell is going to be, and I'm gonna run commands there. Number 1 is where the daemon is going to be run, and it's actually going to run all the CBSD commands that shell tells it to. Uh, Number 2 is web backend. Yeah, the 0 and 1 or C++. 2 is Python and it's backend, web backend, where the REST API is. And number 3 is JavaScript and React. And we're gonna see how it all looks. Well, today we're gonna stretch the surface a bit. Um, so I just run the daemon here, Actually, no. How about I show you what's how they communicate first? So there's a very special directory on my host. It's called Warren CBSDng, and that's where the daemon is going to create a Unix socket, and backend and shell are going to communicate through that Unix socket to the daemon and tell it what to do. Sorry. So you can see that there's nothing inside that directory right now. And the funny thing is that number zero is inside a jail called daemon, and number one is on my host running as root. So this is inter-process communication at first hand, and communication between host and jail processes using that Unix socket. So yeah, we can see this is empty, but once I start this, this shouldn't be empty anymore. All right, and now the sorry, the shell is going to communicate with the daemon through that Unix socket, and it's gonna tell it to for ls. It's gonna tell it to run two commands, JLS and BLS. So that's why we have maybe actually better if I remove this for now. Okay, this is better. So we have a color coded, is it on and off, or there's maintenance also, but I'm not creating anything right now, so there's no maintenance. And the first part is for jails, and the second part where only FreeBSD 1 is um, for Beehive virtual machines on FreeBSD. So there are only three commands for now: ls, start, and stop. So this is how it looks like with a new shell with the CBSDng. If you start and stop something, uh, it's actually and should be the same as running CBSD command on its own. Because, okay, let me demonstrate that. So if I say jstart this jail, right, it looks exactly the same. And that was the idea, to have the shell that can be running on the host or inside the jail, because FreeBSD has ability to uh, be configured so that if you log into that box, into some box running jails and, for example, CBSDng, uh, you can be put into jail right away, and you don't even have the access to the actual hardware or, well, operating system. You only have the access to a certain jail, and you can communicate with outside world through that Unix socket. And although jail has a pretty good set of tools to restrict process, this can restrict it even more because it cannot run, well, almost nothing except the CBSDng commands. So this is cool for the appliances where you have a dedicated shell just for the few things, right? And well, I come from sysadmin world, and less privileges means less opportunity to screw up something. So I like that concept a lot. Uh, so yeah, this is how start looks like, and this is stop. So pretty much we are mimicking what's going on with the CBSD with this code for now. So let me show you now what's under the hood. Uh, Actually, no, I didn't finish. Just a sec. Right. So I'm gonna go and visit this link, and it's a front end built inside its own jail, and yeah, backend is its own jail. So I have three jails and a host, and let me just switch screens. All right. So this is the default landing page of the Freenet, and it's a framework I developed using um, Flask and React and bunch of technologies that I can yak about for ages. But let's see jails in action. So these two come with users and roles. Simplistic management comes with a friend, and you basically have only one user at the start and no roles. But instances are actually important. Interesting. I mean, because if you let me just see, it's almost readable. Let me increase that a bit. All right. So you can see that it corresponds to the list of jails, but you don't have the uh, indication if the jail is on or off. Uh, I mean, all of this is because this is a 2 weeks old project, and we are not nearly ready for prime time. So I'm demoing what is there for now, and there are a few interesting technologies. So this is where I've got with the web, because the path is interesting. CBSD has to be run, then output redirected through the Unix socket to the backend, through the REST API into the React store, and then onto the screen. It's quite a journey for list of jails, right? So let's see what's going on under the hood. Uh, this is not all right. Now, this is what gets all the services up. So, yeah, I have three services. Basically, this is not a service, but it doesn't matter. This is what makes those jails boot and give you the development console with the Tmax and everything. So let's start from the beginning. There is let's just pretend that there is only a shell and a daemon to make things simple for start. So daemon, what it does, mm, it comes with one class that is for exchanging messages between daemon and the client's either shell or web interface. I mean, web interface being Python in the backend doesn't use this class, but it does pretty much the same thing, communicating with the backend. So these are some of the operators and functions that are implemented just to make the life easier. But this is actually important. ID of the message currently unused. Type. I'm gonna talk about this. And the payload. It's actually what you typed on a keyboard or what CBSD output is spewed out, or so needs to be displayed and so on. So they're helping functions, but I wouldn't bother myself with them today. This is what's important. So every message carries uh, three things that are information what happened. So one of the let me see. How should we start? Let's start with this. How does one program actually start? So this is how the daemon starts. And let's see. This is for parsing options. Minus D means demonize or go to background, and minus S means which socket path should I use, and this is the default one. And this column means that S has argument, right? Minus D is on its own, but minus S, then something is a path, and I think it's the least interesting part because get_opt gives you from the arguments to your main, gives you what happened and what you should do, and if the option has an argument, this is how it's called. So you just assign, save it somewhere, and so on. So this is where this while loop is where the options are parsed. For now, only two, but this is how it's done. And if it's a daemon, this needs to happen. And 00 means that inputs and outputs are going to be directed to, I think, dev null. Anyway, it's not gonna output anything. That's what 00 means. Uh, in development, I don't use this option because I want to be able to restart it easily with Control C and run it again and so on. While in production, you're probably gonna use service to store it with dash D. So it's gonna be a real service. Anyway, I create a socket then wherever either default path or whatever you gave me, and then this is where all the magic happens. Uh, Wait for client means that anything connecting to a Unix socket is a client for this daemon, and this is while waiting for a connection. If there was, eh, I hate negatives. Okay, if when client is -1, that means there's an error. So if there's no error, that's what it says. If there's no error, spawn you asynchronous worker and tell it who connected to this variable, and it's the worker is going to use that to communicate with the client. Under the hood, the client is just integer, So nothing fancy actually is going on here. It's a result of a normal open operation in a function in C. So yeah, I'm just opening a socket and then it looks like I'm having a bunch of memory leaks with this async worker, but actually it knows how to clean up after itself. Uh, but that's a fairly complex topic, and let's see if we're gonna cover it today or some other time. But yeah, the this actually knows how to delete whatever needs to be deleted after communication with the client is over. Let's say shell executed ls, it got the output and then said okay, end the program, and ending the program closes the connection, which notifies the worker, and it knows how to clean up after itself. So socket is actually, I got some exercises left over. Okay, so uh, if you ever worked with the Unix sockets, this is actually how you open them and handle errors, and there is absolutely nothing new here. I just honor what was given as an argument, right? Default or otherwise. So uh, this is pretty standard, and this line actually shouldn't be here, but yeah, it's a leftover of one of the experiments. So yeah, once the socket is initialized, it's used somehow. Uh, I'm gonna get to that in a minute. It's used somehow, and then it's deinitialized by this destructor, right? And it calls cleanup because sometimes it's easier to have like init and cleanup functions because you might call them in different places. But yeah, the constructor and deconstructor are actually doing all the work. So this is a delete file, and then if I haven't already close the Unix socket, then close it, and with -1 denote it's closed for future operations maybe. And waiting for client is basically this. It's also C, not C++. There is some indication that I think C++, some standard, should have its own socket class, but I don't know much about it. Uh, by then, yeah, this is how we're waiting for the connection, and once the connection is established, we either say there's an error, or we say, okay, here are the client, communicate with it. Now, all the communication is done uh, through the worker, not. I mean, the socket is used to communicate, but the part of code that is communicating with the client is actually on the worker side, and the worker. Okay, let's see it like this. Right, socket doesn't have much. It's a really simple implementation, but the worker is much more complex because it's going to spawn the CBSD, is going to capture the output, it's going to communicate to the Unix socket, it's going to do all the work. So yeah, worker. and we have a little bit of the how to say metadata for this class, meaning the mutex and thread and condition variable, so it knows how to clean up after itself, and there's no race condition between them and so on. So async worker is okay. Let's start simple. When the socket waits for client and the client is connected, is it gonna create an async worker with this integer, right? The client, and then some internal structure for this async worker called thread is going to be initialized with underscore process. That's this function. What it means is that this function is going to be ran in the background. So the main thread remains free to do whatever needs to be done. And actually, that's waiting for a new connection and handing it to a async worker, and then it communicates with the other client and so on. So what it does is run the actual processing command, the function, and then notify adds this thread to the list of threads that have finished and say, hey, somebody, can you clean up after me? I've cleaned everything else. Can you clean this finished and so on? Because one thread cannot call delete on itself. Well, that's an error. So you have to notify someone. Hey, how about you clean up a bit after me? Just call my uh, uh, destructor, and it knows what to do. And that's joining the thread. That means wait for the thread to finish if it hasn't, and if it has, just slip through it and then do cleanup. The cleanup for async worker is really simple. Just close the connection to the client because this will notify the client that something has happened, and one variable is going to be -1, which will mean to the client or shell or web backend that connection has been closed, and that's how it communicates. So the process actually does a little bit of parsing and then execute. You see, it's sorry. You see, it says 99 lines and process it 27. It kind of gives us the clue where all the implementation is. Okay, so what does process do? This is uh, okay. Read whatever the client sends as a first command because the client has to send first command to initiate the communication. And then if there's an error, just clean up and finish. Uh, and what happens here is shortly put, this message needs to be assembled, and this is what's going on here. Uh, and that message is handed over to execute function to actually execute what's needed. Uh, what happens here is that I will say, for example, ID is 0, type is 0. I want to run ls command and no, let's say, well, okay, I want to run ls command, and this is how the byte stream of this message is going to look like. I can say ls minus l or something like that, right? Uh, no, actually, I can't. For Rails, I cannot. But I can say stop, and this is not a valid command because stop what? So I can say jail 1, jail 2, and this can be a list of jails I will stop. So this is what is going on here. This ID and type are these 00 in this example, and the rest is actually a command for the CBSD to execute. This is how message as a stream of bytes looks when it's uh, transported through the Unix socket. This is what backend, what daemon and the clients are exchanging. So this as well, you can even imagine this is a string, and this string is actually parsed into ID, type, and payload. Well, data uh, here, and it's assembled into an object that is executed as a CBSD function, and it's done like this. So wow, this is the core of the whole operation. This execute actually, this is where the rubber meets the road, and this is what all the input output uh, handling is handled here actually. So by default, prefix to a CBSD command is J. What does that mean? Is that we have CBSD JLS and CBSD BLS, but um, you can tell it. Do you want the command to be run on a jail or Beehive virtual machine by uh, setting the type of the command and the type of, for example, type of Beehive command is this. There is jail and there is Beehive, and this is how the message, how the type is communicated. So with the pipes, this is every process in a shell has two outputs: standard output and standard error. So this is the representation of the. We're going to run a CBSD, and then its output and error output are going to be piped back into this process, which will communicate it back through the Unix socket to the client. And to achieve that, it's done through a pipe. So pipe has two ends, and that's why the array has two elements: read end and write end. Read and write. So this is how it's defined. And what happens is initialize those pipes, and then see if we want color or not, if we want beehive or not. This is what's going on here. And then fork. Fork is you can literally visualize it as a fork. Uh, if you imagine a lifetime of a process happening like this, when there's a fork, it's actually running some command, and it's gonna create a new process and continue to run. So it's like a right, like a fork. It kind of looks like that. And a fork is a really magical, funny little function that um, it takes some time to wrap your head around it. So from this point on, okay, maybe there was an error. That's what this PID less than zero means. There was some error, But if there was no error, then uh, you have two processes, and this piece of code is running in both of them uh, at that point. So your code is running at the two processes at the same time, and you don't want that. You want one to be uh, uh, your async worker, normal async worker, as it was before the fork, and the other one you want to be the child and you want to communicate with it. How you do that is if process ID is zero, that means you're in a child process, and if process ID is not zero, then that process ID is inside a parent process, and this PID is actually the process ID of your child. So you can control it, you can kill it, or you whatever. Yeah, this sounds really terrible. Um, so let me just unfold. All right. So for the child process, it's not gonna read from the output. It's gonna use this output to push data to towards the parent process and the async worker. That's well, this part over here, this 34 lines. But you know you're not gonna use them, and you close them right away. It's actually what happens in the parent also, but for the other end, it's never gonna write to the child's output, so you just close it. And then it duplicates the uh, standard output and standard error into these pipes we created before. And sorry. Um, then it assembles the real command to be executed by this function. Uh, I mean, assembles it, parses the payload, and blah blah blah. So in the end, this is what happens. So CBSD, for example, JLS. Let's say this is what it executes before, because this is what the shell sent, and is, for example, ls. This is a prefix, and it's either J or B. And with okay, if you ignore this, row command is then uh, J plus ls that we got from, right. So this is what we're trying to tell this function to execute, and there are some arguments because uh, this function has to have everything broken down into arguments, and this, well, practically this actually payload is just a big string, so we have to tokenize it into the array of vector of arguments and feed it into the function. And when it runs, because of this, it's going to feed its output to the pipe, and then through that pipe, the parent process is going to, I'm sorry, get that data and send it to the client, to either web backend or the shell. But let's see how it's happening, because this is the best API I've ever seen in my life. It's called K event and KQ. It has only two functions and one macro, and it can notify you when whatever happens with files, with sockets, with processes, with everything. what I'm using it for here is to say, okay, this is the set of events. This is the array of events that I'm interested in. So can you tell me when some of them happen so that I don't have to have thread for every single one of them, but just wait on one line when something happens, tell me what happened, and so I can process it. And that's the idea of K event and KQ. Uh, yeah, we close the from the parent side wrong side of the pipe. Sorry. Where we will have for those two pipes, we're going to create two events that we're interested in listening. Uh, we're going to create a kernel queue for them, and I think it's a kernel queue. Uh, and if that failed, we're gonna tell somebody why. I'm not returning here. Yeah, I should. Anyway, this is how we initialize the events and tell it, okay, now UKQ, these are the events I'm interested in. How about I run in a loop and this is where you block me until something happens. And what this does is uh, use this KQ to run, to wait for the either of these outputs. And when some of them has bytes to be read from them, or data to be retrieved, put them in this target event. And we're going to say the target event is only one. So give me one event at a time to process. If something bad happened, then break the loop. Otherwise, in target event data is going to tell us how much data is there. And we're going to have a buffer that is just 1 byte more than that data. We're going to, this identity of a target event is um for sockets and files, it's a file descriptor, just like in a C, read, open, write, close kind of file descriptor, integer. And we're going to read into the buffer, and this is the size of the data that we're going to read. If something bad happened, then just restart the loop because this K event, if something has been closed or something happened to the connection to the Unix socket, is gonna return either -1 or this data is going to be 0. So this is where we break the loop. And if something bad happened during the read, well, just ignore it. And we are going to assemble the message just like we did before, and then we are going to write it to the actual socket to return to the client. Right, we are writing to client this raw data and its raw data size, so it knows how big it is. And this is a way to wait for uh, that CBSD command to finish, to exit. And this is a state, right? It's when you return integer from the main function, this is where it's going to be stored. I'm not communicating that exit state of a process yet. But yeah, this is how you capture it. So this is waiting for child to finish in order to capture the uh, exit code, put it in ST, and it's going to write to the client, hey, the process finished with this exit code. So maybe your shell should exit with the same code too, because something weird happened, right? Uh, so this is how the magic is happening. This is what's underneath the hood, and this is the heart of a problem. Now I want to show you what I'm going to do. I'm actually going to demonstrate a problem with this implementation first. Let me see. What if I do this? Right. So this command also has login. Oh yeah. It has pretty nice help, and every command has, let's say, ls has help on its own. So for login, it says we need the jail that is required, and it's a text. Uh, I think it can be a number too. I mean, the argument can be a number, uh, but let's say we list all the jails, and now I know there's a jail called CBSD, and I want to log into it. All right, and I did. But now when I type something, nothing happens, right? Because if you remember, I'm only redirecting and piping the standard output and standard error from the CBSD. I'm not handling the inputs yet. And that's for a really good reason. You can't just redirect input. In a general implementation, yes, you can. It's just another stream of bytes. It's nothing special. But if you want to implement the shell, you can't just expect everything to work because you redirected the inputs and outputs. Uh, what your normal shell commands expect is terminal. Uh, it's either called TTY or PTY. PTY being pseudo terminal, and that's what most terminals like Xterm or no. What am I using? Alacrity. I can't even pronounce that. Anyway, all the terminal emulators use that, and it's if you want to have interactive commands like shell commands, but interactive, then these terminals are actually needed. And what I need to work on, and actually started already, but it doesn't work yet. Uh, it's okay, allocate a pseudo terminal for this CBSD command, redirect its inputs and outputs, and uh, through the Unix shell to the, for example, shell. And then once the shell is working, then I need to make the web backend working, and that's gonna be really hard because I hate WebSockets. Whenever I worked with them, they were a hell to work with. Uh, I do have experience, but still, I just hate them. And problem is going to be to have the WebSockets communicate to the uh, sort of WebSockets communicating to Unix sockets through some software in between, but that's going to be a problem that I'm going to solve. I know it can be solved. It's just going to be annoying. So sorry for whining so much. So I think this is enough information for today. It's quite a while. It's actually one big chunk of engine that's behind the demon. So it kind of was um, one unit to be talked about. Thank you for watching. Thank NGI for making this possible. And if you like this talk, please, please, please consider the our Patreon page and becoming a patron. Uh, it's We had to move out as a hackerspace from the flat we were renting, and now we're collecting money for our uh, next venue, wherever it is, flat or hangar or something. So when this Corona ends, we start teaching in person, also not only virtually. So please consider it. Thank you for watching and talk to you soon. Bye bye.